This is actually one of my favorite equations, and the reason for that is that this equation is invariant, which means it's the same in all reference frames, and it's constant or conserved. It's the same at all points in time, even before and after some kind of a dramatic particle interaction. For example, there's an interaction where an electron moving very fast comes in and hits an electron that's at rest. Energy and momentum have to be separately conserved, but it turns out that can cause us to get both of those electrons plus a new electron and what's called the antiparticle of an electron, or a positron. It looks just like an electron, but with the opposite charge. Now, we would like to know what is the minimum energy this needs. Well, that's a very hard problem, because I have to account for the energy coming in, I have to account for the momentum of all the different particles flying out, and I have to figure out what is the total minimum energy after these are all flying out. But it's a much easier problem if I consider it in two different reference frames. In this reference frame, I've got the energy of 1. This is electron 1. The momentum of electron 1. And I've got the energy of electron 2. Now, that's a laboratory frame. This particle is shooting into that one. But I could look at this from a frame of reference where both are shooting into each other. And in this frame of reference, it's clear that the least energy will be where all of this energy becomes my new pair of particles, and they finish up at rest. So in the end, I've got an E minus, E minus, E minus, and an E plus, all sitting at rest relative to each other. That's the lowest energy I can have. Now I could just figure out the energy here, and then convert it into a laboratory frame. But this is an invariant, so I don't have to do that. In other words, I can look at this situation in the center of mass frame after the collision, and I can consider this situation before the collision. So before the collision, I have a total energy that's just E1 plus E2. I'd like to put E1, actually I'm going to put the momentum P1 in terms of E1. So E1 is what I'm going to be looking for. And then E2 is simply equal to mass of an electron times c squared. It's just its rest mass because it's at rest. Now I can use this equation to find P1. P1 squared c squared is going to equal E1 squared minus m squared c to the fourth. Okay. After the collision, in the center of mass frame, the total energy is just going to be 4 mc squared, and the total momentum is going to be 0. So I'm going to plug these values into the invariant before and after the collision. So before, I've got E1 plus mc squared minus the momentum squared, which we know is just E1 squared minus m1 squared c to the fourth. And after, the total energy is just 4 mc squared. That's squared. This is squared. Now it's just algebra. I've got E1 squared plus 2 E1 mc squared plus mc squared squared. I subtract off of that E1 squared. This minus hits that minus, so it becomes plus m squared c to the fourth. And it all has to equal 16 m squared c to the fourth. All right, let's see what happens. First off, these E1 squareds cancel. Most of the energy of that first particle, the original electron, goes into maintaining conservation of momentum. That's why those cancel. These two reinforce. That'll give me 2 m squared c to the fourth, which I can bring over here and subtract from the 16 m squared c to the fourth. What I end up getting is 2 E1 mc squared equals 14 mc squared squared. One factor of mc squared cancels. The 2 cancels, leaving me with 7. And I find that that initial energy, I have to come in with an energy that is 7 times the rest mass of an electron to generate a positron. Notice that problem would have been very challenging using anything other than the invariant.